have a friend who now has her PhD, but from about 19 years old to 40 something, she was at home raising children. And when she took her first statistics course in college, the professor asked her if she'd taken previous courses because she was doing really well. And she said, I swear to you, I have never had a math class with letters in it before in my life. And yet, here we are. First letters. P of A, the probability of A is, so that's, all this means is the probability of A. So if you see this P with parentheses A, probability of A. The useful probability rule number one, probability of not A equals 1 minus the probability of A. Because something's going to happen, right? Either an event occurs or it doesn't. There are only two possibilities. And the total probability is 1. Something occurred or it didn't occur. If it didn't occur, then it's 1 minus the probability it did occur, because those two have to add up to 1. Probability of something happening plus the probability of it not happening is 1.0. The probability of one of a set of mutually exclusive events is the sum of the probability of each event. Said that in the last video. This is my lovely daughter Julie when she was 10, and the probability that I will let Julia date before she is 16 is 0. Yes, I may mean mom. The probability that Julie is not allowed to date before 16 is 1 minus 0, or 1.0, or 100%. Now she's 27 and has a boyfriend. If the probability of A and probability of B are distinct non-overlapping probabilities, then the probability of A or B equals the probability of A plus the probability of B. If we had a very large sample of students that we asked how much they liked math, and 24% of them said, I like math a lot, they agreed with that a lot, and 35% agreed a little, then the probability a student likes math a little or a lot is 59%, 0.59, because it's the sum of these two. We also saw an example of that in the last video with the probability of selecting a child who is 8 or older. Probability and independence. This is important. It comes up a lot. Two variables are independent if the probability of A and B of both occurring is the product of the probability of A times the probability of B. So the probability that a Native American lives in California is 0.12. 12% of all Native Americans live in my home state right here, California. The probability that a Native American in the US has diabetes equals 0.15. So the probability that a Native American both lives in California and has diabetes is 0.12 times 0.15, or 0.018. So 1.8% of all Native Americans live in California and have diabetes. This is assuming that there's no difference in the prevalence in diabetes in California among Native Americans everywhere else. That would be a hypothesis we could check. Why does this matter? Why is this important? Well, if only 1.8% of all Native Americans both live in California and have diabetes, then we shouldn't have a national preventive health program for Native Americans focused only on people with diabetes living in California. Now, you might think that's obvious, but I can assure you it is not. As someone who reviews grants, I very often see proposals for research or service programs that have only a tiny probability of reaching the people they are intended to serve. So when a program is proposed, ask this: what's the probability this will impact the students it is intended to serve? If a program for students with special needs focuses on blind students, what percent of your students within special education are actually blind? Independence again. Two events, A and B, are independent. If the probability of A given B, so here you are again with some letters. This means the probability of A given B. If the probability of A given B equals the probability of A, or if the probability of B given A equals the probability of B, then they're independent. So if the probability of A given B is equal to the probability of A when you don't know B, then the two events are independent. Let's look at an example of that. Here we have, I computed this myself today using the California Health Interview Survey from 2018, where they almost 21,000 people. Now, out of those people, 12.89% were diabetic. So that is a probability of 0.1289. Out of those who answered yes to the question, are you Native American, 18% have diabetes. So another way to look at this is the probability of diabetes equals 0.1289. The probability of diabetes given that someone is Native American is 0.18. So those two are not independent because those two probabilities are not equal. Another way to look at it is if the probability of B given A equals the probability of B. So the probability of being Native American is 0.0484. 4.84% of people in the state are Native American. The probability of being Native American, given the condition that somebody has diabetes, is 0.0676 or 6.76. Again, not the same. Therefore, having diabetes and being Native American are not independent, at least within adults in the state of California.